Hello, everyone. Welcome to the presentation of our work, DSAGEN, Synthesizing Programmable Spatial Accelerators. This is motivated by the emergence of specialized accelerators, which occupies 20% to one-third of the publications in top conferences last year. Designing a specialized accelerator not only requires us to study the behavior of the target application in order to derive specialized hardware mechanisms, but also often involves a full-stack implementation. When the target applications shift, developers probably need to go through this whole engineering-intensive process again. What makes DSAGEN unique compared to prior work is that it can automatically develop specialized accelerators for a set of input applications with moderate human intervention. Our approach to programmable accelerator design automation is the following. A set of target applications are fed to a compiler. This compiler generates multiple versions of the program IRs that take advantage of different hardware features. Our Design Space Explorer evaluates each version of the IR on the candidate hardware, and then it uses the most proper version to guide the design space exploration. Finally, it generates the proposed hardware. In the rest of my talk, I will elaborate the three key components of our framework: the design space of the hardware, the compiler, and the design space explorer. Let's dive into the design space, including hardware primitives and how to compose the hardware. In order to decide the scope of our design space, we studied many prior programmable accelerators. These three are representative. We notice that all these three accelerators tend to follow a decoupled spatial paradigm. By decoupled, we mean that computations and memory accesses are decoupled and specialized respectively. By spatial, we mean that the storage, computation, routing, and timing is exposed to the ISA. Moreover, these architectures can be composed by connecting very simple hardware primitives. These architectures are attractive to us because of their efficiency and modularity. The basic principle of our framework is to represent the hardware in a graph of these simple primitives, so that the compiler can use them as an abstraction during the program mapping. To program an accelerator with such programming paradigm, we need to decouple the computation and memory accesses in order to map them to the corresponding hardware component. The computations are represented in a data dependence graph and mapped onto a spatial architecture, which consists of processing elements for performing the computations and switches for routing the dependencies. The memory accesses are encoded in control intrinsics issued from the control host to the memory controller. Then the memory controller sends memory requests so that the data can stream through the spatial architecture to execute the program. When multiple data streams need to be synchronized, a synchronization element made of coordinating FIFOs will ensure a proper timing. I will discuss the design trade-offs of the key hardware primitives in the next few slides. We support PEs with different execution model because they enable trade-offs for different workloads. Specifically, there are two dimensions. Is it dedicated to only one instruction or shared across multiple instructions? And is the execution timing static or dynamic? These two together enable a trade-off between flexibility, performance, and hardware cost. Systolic PE is the simplest, which is dedicated to only one instruction with the static execution timing. Thus, it requires delay FIFOs to match the timing of data arrival. Another option is to share the PE across multiple instructions, which allows to offload more instructions, and it requires a larger instruction buffer as well as the register file. To enable data-dependent control flow, we need dynamic PE scheduling. Ordered data flow architecture allows this for dedicated PE, and tagged data flow enables this for shared PEs. Tagged data flow is the most general and expensive one, which requires both a larger instruction buffer and tag matching. A single design may only have one kind of PE, or it can combine multiple kinds of PEs for further specialization. Another parameterizable component is the memory. The capacity and the bandwidth are very basic parameters. An advanced feature is to support parallel indirect memory access, which is a very common idiom. We add crossbar to route the request to the corresponding bank and the reorder buffer. Furthermore, we can optionally support atomic updates by adding functional units to banks in situ. Our framework can approximate a wide range of architectures, including programmable architectures and some domain-specific architectures that uses the same primitives. Also, we can represent some custom irregular architectures tailored for very specific applications. At this point, we want to clarify that there are a number of limitations in our current design space that prevent us from closely approximating certain designs. For example, we don't perform speculative execution, which prevents us from approximating dicer. These limitations are classified in our paper. We also want to clarify that our goal is not to replicate all the prior accelerators and their software stack. Rather, we define an interesting and useful design space that can be understood by a general-purpose compiler. Here we come to the compilation. In this section, I will mainly explain how we come up with a unified high-level abstraction and how the compiler supports the diverse underlying hardware features. We have a wide design space, so our programming language should also be generic enough, which means a domain-specific language like Halide, TensorFlow, and TVM does not suffice. Instead, we adopt C. The key challenge here of using C is how to have sufficient information while using a general-purpose language targeting to a decoupled spatial architecture. In order to do this without massive compilation effort, we rely on programmers to provide these hints. Which portion of the code should be offloaded onto the spatial accelerator? Which portion of the memory accesses can be decoupled without hurting the semantics? And which set of the offloaded regions should be concurrent? Here is the example of programmer hint. The offload pragma indicates the loop body will be offloaded onto the spatial architecture. The stream pragma is very similar to the restrict qualifier in C, which means the memory accesses under this loop level will not overlap each other if they start from different pointer. And the config pragma means the offloaded region in this compound body are concurrent. With the hint of these pragmas, the compiler can decouple the computation and the memory access, as well as exploring the transformation space by enumerating the unrolling degree. So far, we have the computation and memory address decoupled. The next major concern is that how can the compiler take advantage of the diverse hardware features, especially considering certain hardware instances might not include some features. We use a modular compilation approach where the basic strategy is that each hardware feature that requires a specialized transformation always has a backup so that it can generate a simple transformation without using that feature. As an example of modular transformation, consider a program which would benefit from parallel indirect memory access. When this feature is available, the compiler will generate memory intrinsics that expresses the parallel indirect memory accesses. Otherwise, it will fall back to scalar intrinsics to guarantee the success of compilation. Other modular transformations include the dynamic control flow for dynamically scheduled components, and offloading code regions with relatively lower execution rate and a larger data dependence graph onto shared PEs. The last missing piece in the compilation is how the decoupled dependence graph is mapped onto the spatial architecture. We use this algorithm to map a data dependence graph. First, map the instructions to the feasible PEs. Second, route the dependence edges through the on-chip switches. Third, if certain PEs adopt a static timing, we need to match the timing of data arrival. If one of these steps fails, we simply unmap some instructions and try each step with randomness again. We repeat it iteratively until the objective converges. The objective captures high throughput and low latency. We are done with the design space and the compilation. Now we explain how to integrate them to the Design Space Explorer. Overall, we use a simulated annealing algorithm to search the design space. At each step, the Design Space Explorer evaluates each version of all the programs on the candidate hardware to select the best suited version of each program. This requires mapping the IR onto the ADG. Then it calculates the objective by considering the performance of the selected version and the area of the hardware. If the objective has improved, then we are more likely to keep the current ADG. Otherwise, we revert it back. To create a new ADG for the next iteration, we either add new components and connect them, remove existing components, or modify the properties of some components. Since the modified hardware may break some of the spatial mapping, we need to remap them for the next iteration. Because we frequently modify the hardware, we need to calculate the objectives many times. This means we need a rapid way of estimating the performance and area. The main performance improvement of decoupled spatial architecture is the instruction level parallelism on the spatial architecture, and the ratio of data availability determines the number of active dynamic instances on the accelerator. Thus, we count the number of instructions offloaded and time it by the data availability ratio to estimate the performance. The model has mean 7% error and with maximum error 30% comparing with our simulated results. Moreover, estimating the power and area by synthesizing the design is too time-consuming. So we build a regression model. All the parameters in this model are collected by synthesizing each single component with different parameters. This approach can accurately predict the hardware cost comparing with the synthesized numbers. The main source of the error are the buffers injected to meet the timing. After optimizing the objective function calculation, the iterative spatial mapping algorithm dominates the execution time of DSE. To address this, we have the insight that remapping the whole data dependence graph is not necessary. We only need to repair the mapping components impacted by the hardware modification. This example shows a scenario in which the compiler is considering two versions of the program, where one of them is unrolled. The Design Space Explorer chooses to eliminate the bottom right PE. The first version is not affected by the modification at all, so the mapping still remains correct. The second IR is affected in that one of the adds maps to a PE no longer exists. Therefore, we need to assign a new PE for it and reroute the dependence. This scheduling repair technique saves the significant compilation time during DSE. After the design space exploration converges, the last step to generating the hardware is to decide the software-hardware interface. An important aspect to this is to determine how can we quickly configure each component of this spatial architecture for a program phase. We decide to reuse the data path for configuration by adding a config bit to the spatial architecture. When this bit is enabled, the data packet goes to the red paths to load the data configuration bit stream. Then the question becomes, how can we generate these paths? We use a heuristic-based adjustive algorithm to generate these paths. Each time we pick up the longest path and randomly cut some of the nodes and connect them to a shorter path to see if the longest path of all gets shorter until it converges. Comparing with the ideal lower bound, this algorithm introduces only 40% of the overhead. Here we come to the evaluation section. We first clarify our evaluation methodology and then evaluate two key pieces of our framework, the compiler and the design space explorer. We evaluate the performance of our applications by extending Gem5 in order call with the stream-decoupled ISA and integrating a cycle-accurate spatial accelerator simulator. We evaluate the power and area by implementing our components in Chisel RTL and synthesize this RTL in Synopsys Design Compiler 28 nanometer library at 1 GHz. The memory system is estimated by Cacti 7.0. We stress our compiler with 5 different architectures and 4 different sets of workloads. Software run on Mesh Suite, a benchmark suite for accelerator design. SPU run on 2 micro benchmarks with irregularity, histogram and sorted key drawing. Revel and triggered instruction run on digital signal processing kernels, which are challenging because of their imperfect loop bodies. Mari run on dense linear kernels from Polybench. Here are the performance results. The x-axis are the workloads and the y-axis is the speed up over a x86 CPU with GCC03 enabled. Our compiler is able to get 80% of the performance of the manual tuned version, as it performs most of the important optimizations like decoupling, memory and computation, vectorization, data-dependent control flow transformation, and inter-region concurrency optimization. Most of the performance degradation is from lack of peephole optimization, which leads to some extra control instructions. FFT is an outlier because the stride of memory access at the last iterations becomes too small to fully utilize the memory bandwidth. The manual version can pare those loops down and coalesce the memory accesses. We stress our design space explorer with 3 different sets of workloads. First, the dense neural network layers, including convolution, pooling, and the matrix multiplication. Second, the mesh suite, which we mentioned before, a benchmark suite for accelerator design. Third, sparse convolutional neural network, a single workload with irregularity. They all start from the same initial design, a 5x5 mesh with the full arithmetic control flow and indirect memory capability. And we use the performance square per millimeter square as the objective function. On this slide, we are showing the breakdown of power and area of the initial and the generated designs. Our design space explorer is able to save 40% of the power and area of the initial hardware. Naturally, it's able to select a better set of functional units. More importantly, in many cases, it can reduce the network and synchronization overheads, which is accomplished by creating a custom and irregular network topology matched to the set of input programs. This is a lengthy process. The Design Space Explorer takes mean 20 hours to finish. To sum up, we present an automated flow to generate programmable specialized accelerators. The modular hardware-software interfaces accompanied with a modular compiler that understands each hardware primitive enables the flexibility of design space while retaining a fixed high-level abstraction. Our approach is analogous to high-level synthesis, but for programmable rather than a fixed function accelerator. This is enabled by specializing for multiple workloads at one time in a rich design space. Ultimately, we strive to achieve the same level of specialization as manually designed specialized accelerators, but with the productivity through the automation. There are many remaining challenges, which include expanding the design space, improving the speed and effectiveness of exploration, and enabling richer program transformations. Our framework is under development at the following GitHub link. Check it out if you are interested in it. Please join me in virtual ISCA on June 1st, 5:15 p.m. Pacific time for a lightning talk and discussion. I'm looking forward to seeing you there.